Okay, we are in Chapter 8. What's on the board right-hand side is pretty much where we were last class meeting. We're looking at tube flow. Okay, flow inside of a tube. We are looking at two possible cases. One is a constant wall heat flux, Qs double prime is a constant. The other one is a constant tube surface temperature, Ts equal constant. Let's box that guy in. We talked about those two cases and where they might appear in the real world last time. To get the equation, now each one of these guys has two equations. One gives you the temperature at any position along the tube. The other one gives you the amount of heat transfer that's occurred. Temperature at any point along the tube, the amount of heat transfer that's occurred. We got this equation by looking at a little differential element of fluid in the tube, dx in length. It led to a differential equation, which we solved and got this equation. This is x. This is linear. Okay, that's a linear equation. Okay. This guy here, we took again a small differential element of fluid, dx in length. Solving the differential equation, we got this thing. Exponential variation of temperature with x. Then we got the heat transfer Q and something we defined as delta T log mean. That's called the logarithmic mean temperature difference. Logarithmic mean temperature difference. And here's how we defined it. We drew a picture on the board last time so you know what delta T out and delta T in are. Okay, so that's where we ended up last time. Now, this equation is fine, except the only problem is nobody's going to give us h bar. We're expected to find h bar from Chapter 8 material. So how do you find h bar? Okay, so we'll start over here to get h bar. So to find h bar for tubes, okay, the derivation is, let's do the first one first. Qs double prime equal constant. This is all for laminar flow. Laminar flow, Reynolds number based on diameter less than 2,300. Okay, now, H for this, that guy comes from calculations done in Chapter 8. Takes about a page, a little more than a page to do it. I'm not going to go through it, but what it is looking at, it is equating the conduction at the tube surface, because the velocity is zero there, the conduction at the tube surface, which has a dt dr at r equal r outside, and then the equation for Newton's law of cooling, Q equal h a t s minus t mean. So there's a derivation, takes a page. When you go through that, you end up with this very simple equation. And then if you want to get a Nusselt number based on diameter, which is hd over k, you can do that. If you do that, you get 4.34. It's just a constant value. Doesn't depend on Reynolds number. It just is a constant value. Now, this has to be done for fully developed conditions. Fully developed velocity, fully developed temperature. Okay, so the conditions are fully developed velocity, fully developed temperature, and laminar flow. Properties at T mean, mean temperature. Ts equal constant. Again, you have to go, the book doesn't even go through it, but you have to go through some pretty lengthy calculations for that. The book just presents the answer. The answer, similar to the constant wall heat flux, is the Nusselt number based on D is 3.66. It's a constant. Properties at T mean. Fully developed velocity and temperature for both. Laminar flow for both. Everything in this panel is for laminar flow, fully developed velocity, fully developed temperature, and properties at T mean. Those two equations. You want to find H? That's how you find H. Where does that H go? Over here. For Ts equal constant, you put that H right here, where the H bar is. You put the H down here for the Q calculation. You get the H from that, if it's fully developed velocity, fully developed temperature, and laminar flow. Mm-hmm.
Is the top for QS constant or QS double constant or TS?
Yeah, this guy here is for that guy. This guy here is for that guy. Is that what you're thinking? Okay. All right. Now, let's just look at the tube flow again. Here's the tube flow. What's entering here is T mean in. And as we said before, as the flow enters the tube, boundary layers develop around the perimeter of the tube. The temperature boundary layers then eventually meet at the center line. That distance is called X fully developed. That's the entrance region. Okay, now, once they meet at the center, the normalized temperature profiles become constant, and this is called our fully developed region. This is the temperature profiles. I'll draw one here just so you see it again. Here's the surface temperature, Ts. Let's say the surface temperature is hot. Here's Ts, and then the temperatures, this temperature, Tmi, is colder, so it looks something like this. Okay. Now, as long as we're in the fully developed region, to the right of my hand, you can use those expressions right there. Either one of them. As long as you're to the right of my hand, you can use those. Assuming the velocity is also fully developed. Both have to be fully developed. Okay, but of course, in many tubes, that's not true. You're not in the fully developed region. I think I mentioned last time things like maybe oils, especially. They develop fully developed velocity very quickly. They develop temperature over a long time. We also had the one problem. It was a Reynolds number, like it's 1,000. Laminar flow, or 2,000. It was 2,000. Laminar flow, a 1-inch tube. How long did it take to become fully developed? Oh, we found out it took 100 inches to become fully developed with a 1-inch tube that big around. So, a lot of flows in the real world aren't fully developed velocity and temperature. Well, how do we handle those? All right, we'll take one right now. Let's take fully developed velocity not fully developed temperature. Okay, if you do that, the equation for the Nusselt number if you go through the derivation, this is what you end up with. That's the equation we end up with for how do you find h bar if the velocity profiles are fully developed, but the temperature profiles are not. Notice it's still, you start out, oh, by the way, this is for Ts equal constant. So you start out like over here, 3.66, so here it is, 3.66. Then you add something to take care of the not fully developed temperature. This is what you add, this term right here. GR stands for the Gratz number. A dimensionless number. Again, there is a ton of dimensionless parameters in fluids and heat transfer. Right here, we've got 4 of them on the board right here. The Nusselt number, the Gratz number, the Reynolds number, the Prandtl number. Oh yeah, our equations in heat transfer are typically formulated in terms of dimensionless parameters because they're so useful. And again, that's why in ME 312, you spend part of the time going over dimensionless numbers because they're so important to engineers. Okay, properties at T mean bar. T mean bar is the average of the inlet and the outlet. So that's how, now, where do you use that H bar? Go over here. Ts is constant. You would solve for that H bar first, then you'd put the H bar in the equation for the temperature at any X location and the heat transfer over the tube. Okay, third case, not fully developed velocity, not fully developed temperature. That's officially called the combined entry length equations. Neither one's developed. They're both partially in the developing region. By the way, I'll put the equation numbers down here. Okay, this one, fully developed, 53 and 55. This one, 857. This one, equation 858. I'm not going to put it on the board. It's way too long, and it's way too complicated. It's, well, you'll look at it, you'll see. It's not a fun equation. So it's there, okay. Properties of T mean bar. Our author's done a really good job. That's one of the reasons why we use this textbook. He really helps you. He tries to help you. At the end of chapter 8, there is a summary table, table 8.4. It has just about every important equation in chapter 8. It has that boxed equation 4.34. It has a boxed equation 3.66. It has this one right here, 3.66 plus a correction factor. It has this one right here, 858. They're all in there, okay? 858. The good news is he gives you the equation number in the textbook, then he gives you the conditions. Now, this table is on your data package for the final exam. You've got this. Okay? So if I look at this equation here, okay, there it is. Okay, it says it's equation 857. Yeah, that's what I got. It says it's for laminar flow. Yeah, I got it, laminar flow. It said it's thermal entry. Thermal entry. This means thermal entry. Thermal, or temperature, is not fully developed. So the entry region is not fully developed there. That's called thermal entry. This is called combined length. Thermal entry. Uniform surface temperature. Yeah, I said that. It's for Ts equal constant. Big box on top. Okay. It says the Gratz number is D over X Reynolds Prandtl. Okay, gave you the Gratz number. So, this is a nice little summary table. You don't need to page through the whole book to find it. It's all right here on one page. Almost all the important equations. Okay. All right.
What page is that on?
536. Chapter 7. There it is. All the important equations in chapter 7 on one page. It's on your data package. Okay. I can find flat plate equations. I can find circular cylinder equations. I can find a sphere equation. For what? For the delta, bond layer thickness, for the average convection coefficient? Yeah. With all the conditions given, it's laminar, it's the local H, properties of TF. Yeah, they're all right here. So, two tables, one chapter 7, one chapter 8. Author's done a great job of just summarizing things because he knows those chapters are very lengthy and there's a ton of equations in there. And to go through them all is a horrendous job. So he summarized the most important equations in those two tables. Okay, so that's what you've got for a resource. That's your library. Plus, check those against what I put in the board and boxed. The ones I boxed in the board obviously are also important. They might not be in that table. Okay, the other case won't occur. We're not going to consider it. It won't occur. It's the one which is not fully developed velocity, but fully developed temperature. So don't worry about that one. You won't see that on homework or an exam. Okay, so now let's box that guy in. I'm not going to write it down, but I'm going to box it in. Properties at T mean bar. Yeah, same thing. Okay. Let me add one more over here. For what we're doing in this class, we're going to also use Q equal m dot C sub P T mean out minus T mean in from thermal. It doesn't matter. I can use that for this problem. I can use that for this problem. I can use that for either one. It holds for either one. Okay. Everything to the left of my hand is for laminar flow only. Laminar flow only. Everything to the right of my arm is for laminar flow or turbulent flow. Either one. Everything to the right of my hand, that's QS, that's that one over there, and this is TS constant, that's this one, and this one. You don't have these two guys for QS double prime constant, so don't worry about that. You don't have these two guys for that. This is, again, I'll put up here again, this is TS equal constant. Good news is you probably won't need that for QS double prime a constant. Because look at the QS double prime equal constant equations. Do you see an H in them? No, I don't. So I probably don't need them. Look at the equations down here. Oh yeah, I need H bar here, and I need H bar there. I need them. Where are they? Here, here, and here. Okay. All right, laminar flow left of my arm. These guys, doesn't matter, laminar or turbulent. Guess what he's going to be, obviously, turbulent. Yeah. Turbulent heat transfer. Okay. The equation that we need for that, and again, these guys are not derived from governing partial differential equations. Their derivation goes back to chapter 6, but just in a real quick 2 sentences, it comes from the analogy between heat transfer and fluid mechanics. So in the fluid mechanics, you get equations on the for the tube with a surface shear stress, tau, at the wall. You can then relate that to the heat transfer. Okay, that's the Reynolds analogy. It's in chapter 6. You can relate the results of fluid mechanics to heat transfer. You use that to develop these equations. And the only one we're going to use, there's about 3 of them in the chapter, but the only one we're going to use is this equation. Nusselt D bar Okay, and that came from taking experimental data for fluid mechanics and then using Reynolds' analogy to convert that to heat transfer. Chapter 6 stuff combined with chapter 8 stuff. The bar again, what does the bar mean? The bar means the average over the length of the tube L. The average over the length of the tube L. Okay. Now, this guy here, properties at T mean bar. Okay, just like this. This is Ts equal constant, Qs double prime equal constant. Doesn't matter, it's valid for both. You don't need to ask the question, is the tube surface temperature constant or is the tube surface heat flux constant? You don't need to ask the question. One equation handles both. Because turbulent flow is so unusual, it's such a mixing phenomenon that it really doesn't matter what's kept constant, as opposed to laminar flow, which is not serious mixing. So in laminar flow, you have to ask the question. Here's the question. Answer yes or no. Are the velocity profiles fully developed? Answer yes or no. Are the temperature profiles fully developed? Answer yes or no. Same thing here, same thing here. Here's the answers. Yes, yes. Here's the answer. Yes, no. Here's the answer. No, no. That guides you to the correct equation once you answer that question. First of all, get the Reynolds number. First question you answer, is it laminar or turbulent? If it's laminar, everything to the left of my arm. If it's turbulent, between here and here. Then over here, if it's laminar, what question do you ask yourself? Is it constant wall heat flux? Is it constant wall temperature? Answer what it is. If it's constant surface temperature, then you answer the question, fully developed, yes or no. And finally, you focus down on the equation you want to use to solve the problem. That's the way it works, okay? These guys over here, you know, laminar and turbulent, both laminar and turbulent. turbulent only. Laminar that way. Okay, so that's in a nutshell. Those are the equations in the chapter you want to be concerned about. And there's more questions. All this stuff here is for smooth tubes. Most of the tubes in the world aren't smooth. Now comes rough tubes. How do you handle it? Look in the book, it's in there. Go in a search, online search, it's there. We're not going to do it. All of our tubes are assumed to be smooth, okay? Yeah.
Yeah. When you say for heating and for cooling, is that when the liquid is heating?
Now oh, yeah, exactly. Right. Which means, the other way to put it, which means that T surface is greater than T mean in. This one. T surface is less than T mean in. Okay. Now, we're going to work some problems, but I'm going to work problems on Chapter 8 Monday. I'm going to work problems similar, or your homework problems. I'll set them up for you because you're not turning those in for grading. So I'll set them up to make sure you get off on the right track on Chapter 8 homework. I'm going to go over the homework that we passed back today now, though, and mention some problems I saw on that. Anybody need the homework? It came in late? Okay. Back there, too? Okay. All right, so let's take a look at that then. Let's see. My eraser here. Where did I put my eraser? Where did I put my eraser here? Oh, I know. Oh, boy. Okay, I know where it is. Okay. Now, let's take a look at I'm not going to really look at the first two. They're too simple. But I will give you a hint on the first two problems in Chapter 7. This is the homework you turned in, and I just passed back to you today. Okay, so problem 7.1 and 7.2. No, 7.2 and 3? Yeah, 7.2 and 3. Just so to remind you again, what I said. In problem 7.2, I said don't do anything that is stuff from ME 312. We're not going to revisit ME 312 on homework or an exam. So I'm not going to ask you those kind of questions on homework and exam. If you read problem 7.2 with engine oil, it's laminar flow. It says, find the surface shear stress. No, we did that in ME 312. It says, find the drag force on the plate. No, we did that in ME 312. So those two things, don't answer them. Don't do them. Problem 7.3, same rule. Part B, evaluate the surface shear stress. No, don't do it. That's ME 312, surface shear stress. Anything to do with surface shear stress or drag force, don't do it. That's ME 312. All right, so let's go on then, because the rest of it's pretty straightforward. Let's take the next problem, which is 7.17. Okay, 7.17. Let's put that up on the board here. This is a flow over a flat plate. Okay, the plate's at 100, the air is at 50. All right, so we got flat plate. Approaching fluid stream, 50 degrees. T surface of the plate, 100. We're measuring X from here, and the plate length is L. Okay. The fluid's air. Air. Okay, part is really not a part A, but there's two things listed there to do. I'll list them as A and B. Length of 20 centimeters in the flow direction of width of 10. L equal 20 centimeters, W equal 10 centimeters. That's into the blackboard, of course. Okay, Reynolds number based on the plate length is 4 times 10 to the 4th. Reynolds number is rho u infinity 1 L over mu 1. That's what the Reynolds number is. Call it Reynolds number 1. Okay. What's the rate of heat transfer from the plate to the air? So Q equal H bar A S T S minus T infinity. Okay, I know AS, it's 0.1 times 0.2. I know TS, it's 100. I know T infinity, it's 50. Okay, obviously, chapter 7, what's the problem? Find H bar. First thing to do, answer the question, is it laminar, turbulent, or mixed? 3 questions. Laminar, turbulent, or mixed? All right, 4 times 10 to the 4th. That's less than 5 times 10 to the 5th. So it's laminar. So H bar is equal to 0.664 Reynolds L to the 1/2 Prandtl to the 1/3. Solve for H bar. Got it. Plug it in. Done deal. All right. I got Q now. Next, increase the free stream velocity by a factor of 2. Call it U infinity 2. 2 times U infinity 1. And increase the pressure to 10 atmospheres. I didn't put on it, but the pressure here was 1 atmosphere. The problem said the pressure is, the air is at 50 degrees C and 1 atmosphere. Okay. 101 kPa, 14.7 psia, whatever you want to do. Oh, by the way, I'll draw the picture now. It's laminar boundary layer. Okay, that's this part here, part A, part B. Okay, find the heat transfer now. Okay, Q, here it is right here. AS, well, it's 0.2 times 0.1, it didn't change. TS, it didn't change. T infinity, it didn't change. What changed? Maybe. H bar, okay. Find new H bar. All right, to find new H bar, I've got to find, these are all the steps you take. Find a new Reynolds number. Did the Reynolds number change? Okay, let's find out. Reynolds number 2 is equal to rho 2 U infinity 2 times L2 divided by mu 2. Okay, there it is. Okay, let's see. How about U infinity? Okay, U infinity right here, 2 times U1. How about L2? Did the plate length change? No, it didn't change, L1. How about mu? Did mu change? No, it's mu2. Mu1 equal mu2. L1 equal L2. It didn't change. U infinity 2 equal 2 times U infinity 1. Got it. Where does that pressure come in? Well, you know where it comes in right there, density. Because he said, this is air. And how do we model air? As an ideal gas. And what's rho for an ideal gas? P over rho equal RT. So rho equal P over RT. So 1, 1, 1. Rho 2, P2 over RT2. Did the temperature change? Well, look over here. 50, it did change. T1 equal T2. Okay, so put that in here. Equal P2 over RT2, that's this guy right here, okay, times 2 u infinity 1 L1 divided by mu 1. That's a T1, okay. T1. And what is P2? P2 right up here, 10 times P1. Divided by mu 1. Okay, that's equal to 20 times my P1. Let's see my P1. Oh, I got to put this in there, right? My row right here, right there. I got to put the RT1 in here. Okay. P over RT1 is rho 1. Okay, 10 times 2, 20, times rho 1, u infinity 1, L1 divided by mu 1. That's the Reynolds number 1. That's equal 20 times the Reynolds number for 1. Reynolds number part A was 4 times 10 to the 4th. 800,000. So that's my new Reynolds number for the pressure increasing by a factor of 10 and the velocity going up by a factor of 2. What happened? Oh, this one right here, less than 5 times 10 to the 5th. It's laminar. This one right here, greater than 5 times 10 to the 5th. It's mixed flow. So now I go to the mixed flow equation, which is in your notes in the book. And I find h bar, and I put h bar back in that equation right there. Get Q equal h bar A surface T surface minus T infinity from the mixed flow equation. But I'm just showing you, the main thing is, how do you get that new Reynolds number? How do you get the new Reynolds number? Okay. You write out the Reynolds number there. You do what he says. Double the velocity, increase the pressure by 10. When you increase the pressure by 10, and here's, write down ideal gas equation of state. There it is. Did the pressure go up? Oh yeah, 10 times. Did the temperature go up? No, it stayed constant. So the density now, if the pressure goes up by 10, the density goes up by 10. There it is right there, 10. Here's the catcher. Oh, how can you say that? How come the absolute viscosity didn't change, mu2 equal mu1? Well, the first week of ME 311, the first chapter of our fluids textbook says in there, for an ideal gas, the viscosity, the absolute viscosity, is a strong function of temperature, but it's not a strong function of pressure. Okay, there it is. Fluids textbook says that the absolute viscosity, mu, is not a strong function of pressure. Conclusion, it's not going to change when you increase the pressure by 10. It stays the same. Does the density change? Oh yeah. Why? Because you see pressure right there. Okay, that's the big long story of how this problem should be set up to be solved, okay? All right, if you want to go to the back of the book and you want to look for air in the tables, there's air, okay, table A4, air. And you want to find mu to put in there. There's mu right there at the film temperature. There's mu. I pull the value of mu out of that table. Now there's a column rho. There's a row column there too. But you better read the top of the page. These are the properties of gases at atmospheric pressure. Conclusion, do not use this table if the values of pressure are changing. Don't use the density from this table. It's changing. But because of fluid mechanics, chapter 1, ME 311, they said mu is not a strong function of pressure. So these properties are for atmospheric pressure. They can be used for the pressure 10 times atmospheric. The mu column right there. Okay, so big, long story, but that's how you solve that problem. Okay, any questions on that guy then? Okay, let's go on to the next one, 720. I think I'll put 20 right here in the middle. All right, 720. This is the refrigerated truck. All right, let's draw the picture of how this guy looks. Let me go to the chapter and kind of read it again. 720. Oh, yeah, okay. He tells us there's two thin sheet metal. The top, the roof is two thin sheet metals, and they're covered by, or between those two, sandwiched in there is insulation. So here's the model of the top of the trailer of the truck body. So this is the insulation in here. And these two guys here are the skin on the inside and the outside of the truck body. So that's aluminum alloy panels. Aluminum alloy. And the stuff inside of here is supposed to be kept cold, so its temperature is minus 10 degrees C. This is a refrigerated truck. Keep the stuff inside cold. The top surface of the truck body, trailer, is exposed to sun. It's the middle of the day. So here comes the solar radiation, G. That's called the irradiation. He says that the air outside the truck body is at a temperature, we know all the links, we know all the aluminum panels. What do we have for that? Let's see if we're given that. I think we are. Yeah, there it is, 32 degrees C, air temperature. T infinity, 32 degrees C. Okay, so let's assume that the top surface of the truck body gets hotter than the air. That's a reasonable assumption. So from the sun, well, it can work either way. You don't know this top surface. Call this temperature here T1. Call this temperature here T2. Oh, I know T2 is minus 10. Give it to me. I don't know T1. Maybe it's less than 32 or greater than 32. I'm going to say that it's less than 32 for right now, just right now. So what comes into here now is convection. What goes out of here is radiation. Okay, and so this is Q radiation. Okay. And you're supposed to find the temperature of the top skin of the truck, T1. Find T1. And then find the heat load, Q. The heat load is how much heat gets into the truck interior. Because then you have to size your air conditioner for the truck. The heat load then tells you how much heat goes through here, gets into the inside of the truck body, because your refrigeration unit has to take that heat out. Okay. Go back to chapter 1, energy balance. E dot in minus E dot out. If I want, I can maybe do it for the whole thing, E dot gen equal E dot storage. And maybe I'll do it for the whole top of the truck. Not a good idea, because I know what's coming in and going out the top. I know those Q's. At the bottom, I don't know what those Q's are. Is that convection, radiation, or what's happening down here? I have no idea. So I'd soon convince myself that I don't think it's a good idea to draw a control volume around the whole top of the truck, because I don't know what's going on in here. I don't know the interior temperature of the air in there. It's not -10. So you're left with conclusion. If I want to find T1, I think what I'm going to do is I'm going to draw my control volume on the top surface of the truck, a surface control volume, chapter 1. Okay, get rid of those two terms. Chapter 1, a surface control volume looks like that. It's a top surface control volume. Okay, let's see, the top surface, what comes in? Let's see, irradiation G and the convection. How much of G is absorbed by the top surface? Alpha G, absorbed radiation. He gave me alpha, I know alpha, he gave it to me. What else comes in? Convection, okay. H times the area, I'm going to do this on a per square meter basis, so H times T infinity minus T1. What goes out? Radiation plus epsilon. He gave me epsilon in the problem. I know epsilon. Sigma, T1 to the 4th. I don't think it's going to be much of a problem, but I'll leave it in there. It is leaving the top surface. What else? Oh, there's conduction from the top surface down that way. Conduction, okay. This is a minus sign because it's going out. Now we have conduction. Conduction, chapter 3. This is a 3-layer in series combination. Aluminum, insulation, aluminum. High temperature, T1. Cold temperature, T2. Divided by R total. L insulation over K insulation. This is on a per square meter basis. Plus 2 times L aluminum divided by Ka, but A is 1 aluminum. So there's our total. And that's equal to 0. Solve for, I know everything, solve for T1. But you better make sure you don't make a crazy mistake on an exam. You do not want to leave that guy 32 degrees because this guy has to be absolute. So everything in that equation with a capital T better be an absolute, except, yep, I don't know this guy, I don't know this guy, I don't know this guy. Oh, I forgot, I don't know H bar either. Oh, okay, that's why you're in chapter 7. Okay, so let's read the problem. Oh, thank you very much. He says, turbulent flow may be assumed over the entire length. All right, I got it now. Chapter 7, turbulent flow over the whole length. Assume turbulent flow. All right, get the equation. Nusselt D equal for turbulent flow. Calculate H bar from that equation. When you get H bar, put it in there. Done. Okay, so that's how you, now, every problem I'm choosing here is a good review for the final, because where did we start out? Here it is, chapter 1. What's this guy right here? Series resistances, chapter 3. What's this H over here? Chapter 7. One problem. Chapter 1, chapter 3, chapter 7. Okay. This guy's chapter 1 here, you know. This guy's chapter 1. This is mentioned in chapter 1. I know I saw it. But this guy's chapter 3, series resistances. if you don't know which one, if T1 is hotter or colder than T infinity, if you don't know it, because you don't know it to start with, change this sign over here for convection, change the sign, solve it again. One solution will probably give you reasonable numbers, one will give you kind of nonsensical numbers, so you'll know when you solve it which one's the right way. So take your normal feeling first. I think that may get hot from that G up here, so I'm just saying I think that it's going to be hotter than 32. So I put it like, I flip-flopped it, didn't I? The other way. T infinity hotter than T1. Yeah. Colder, not hotter. Oh, and then part B. You want the heat load? There it is right there. This is how much gets down to the inside from here. That gets down to the inside. That's what you've got to take out by an air conditioner on the front of the truck trailer. Okay. All right, so that's that guy. Any questions on that one? Okay, let's see if we have time for one more. Yeah, we do. All right, let's look at 724. All right, 724 is steel plates. We know it's AISI, whatever it is, 1010, yeah. All right, so we have these steel plates. They look like this. And the air blowing over them like this. So if you want to look at the plate on the side, it looks like this. This is L. This is W. Okay, taking one plate. Air's on both sides, so there's a boundary layer on the top and the bottom. And here's the approaching T infinity. Let's see what we're supposed to find here now. Part A. We know it's air, we know it's temperature, we know it's velocity, we can find the Reynolds number. So we find the Reynolds number. Based on L, on the dimension L, it's going to turn out to be laminar. Q from one side, 0.664, Reynolds L to the 1/2, Prandtl to the 1/3. Okay. Yeah, I think that's all in there now. What's the rate of heat transfer from the plate? If the initial plate temperature is 300, it's really hot. The air blowing over it is really cool, 20 degrees C. Yeah.
The Q one side be the new salt.
One side, Q both sides equal 2 times Q one side.
Well,
So, laminar. Now, what do you say? I'm sorry.
that equation, that's for the new salt number, not.
Oh, yeah. Thank you. It is. So let's put new salt up there. Thanks. And so this is 2 times H bar times the area is W times L. T infinity minus T surface. Right. Thanks. Okay. Now, second part. What's the corresponding rate of change of the plate temperature? Okay. Corresponding rate of change of the plate temperature. Okay. Here we go again. Problem 720. Chapter 1, surface control volume. Chapter 1, I'm going to take the whole plate as my control volume. So energy balance. On whole plate. All right, E dot in minus E dot out plus E dot gen equal E dot storage. Okay, look at my plate. The plate comes in hot. It's being cooled by air blowing over it. Okay. Any energy come in? No, zero. Energy goes out? Oh yeah, by convection. Generation? No. Storage? Of course. Okay, minus E dot out. I know the area, so it's H bar. There's two sides again, so 2H bar times the area, W times L. It's right there. T infinity minus TS. That guy right there. Storage, M, C sub P, dt, d time. That's what I'm supposed to find. How's the temperature vary with time? Okay, what is the mass, the density times the volume? Do I know the density? Yeah, I know the density. It's in the back of the book for steel. Okay, got it. So solve that guy for dt d time. Okay. Chapter 1 again. Realize what E dot storage is, MC sub P dt d time, and then get H bar from up here, chapter 7. So chapter 1, chapter 7, and what's E dot storage from chapter 1 too. Okay, I think it's a good stopping point. So we'll stop for today. We'll